Hi everyone, in this video I'm going to address the issue of whether a set forms a basis for a vector space. So first of all, let's look at some standard bases. For P2, the standard basis is made of 1x and x squared, because if you multiply these polynomials by constants and add them together, you can generate any polynomial of degree 2 or less, right? So the standard basis for P2 is made of 1x and x squared. It has three vectors, three objects in it. So now the word for vector is now a more general word, and it means anything in the vector space. So the dimension of P2 is 3 because the standard basis for P2, or any basis for P2, contains three vectors. So we talked on the virtual class last time about the standard basis for R2, that's just I and J. The dimension of R2 is 2 because the standard basis contains two vectors. We also saw the standard basis for M22, that's 2 by 2 matrices. The dimension of the vector space M22 is 4 because the standard basis has 4 objects. So now these matrices are, all of these things are called vectors. The polynomials are called vectors, these are called vectors, if in the context of these three sets being vector spaces. So similarly, you might guess that P3, that means the set of polynomials of degree 3 or less, the standard basis for that is 1x, x squared, and x to the third, because you can span all of P3, you can generate any third degree polynomial by taking combinations, multiples of these vectors, adding them and subtracting them together. And so the dimension for P3 is going to be 4. So this is something to remember. The dimension for R2 is 2, the dimension for R3 is 3, the dimension of P2 is 1 more. So it's 3, the dimension for P3 is 4. Now there's a theorem in section 4.5 that states that every basis in a vector space must contain the same number of vectors. So because we have a basis with 2 vectors in R2, we cannot have another basis in R2. We can't have a set that generates all of R2 that has 3 vectors. Now let's look at what is and what is not a basis. So here is this set containing 1, 2, 3, 4 vectors. Do you think this is a basis for R3? Well, it might span R3, but it doesn't form a basis. It's not the minimal number of vectors that you need to span R3. So that's what a basis is. It's the minimal number, the smallest number of independent vectors that can span, that can generate all of the vectors in that set. So because the standard basis in R3 has, I didn't write it down, has 3 ijk, right, 3 vectors, then the answer here is no. The dimension of R3 is 3, and this contains more vectors than that. So the set contains too many vectors. So we don't really care about whether they're independent or not, they span the space or not. There's too many vectors for it to form a basis for R3. So let's see, is this set, similarly, is this set made of 1 plus x, 1 minus x, and these 2 other vectors a basis for P3? I'm sorry, the question I wanted to ask, is this a basis for P2? So they're all polynomials of degree 2 or less, right? But a standard basis for P2 contains 3 vectors. The dimension of the vector space P2 is 3, right? So the dimension of P2 is 3, this set has more than 3 vectors, and so it is not a basis for P2. Would it be a basis for P3? It would not, because it doesn't contain any term of degree 3, right? So it would not be able to span P3. So I'll show you how to determine what vector space a set generates in the next video. Is this set a basis for R2? Well, R2 has dimension 2, so we're on the right track with this. This set contains 2 vectors. Now, in order for a set to be a basis, it has to span R2 and it has to be linearly independent. So both of those computations, so if you want to show, does it span R2, and you want to ask, is the set linearly independent? So right now, this is what we need to compute. We need to check both of these conditions in order to figure out if the set forms a basis. So is the set linearly independent would mean how many solutions does this system have, right? Does this only have the trivial solution? That would result in the 2 vectors being linearly independent. But wait, we have another way of telling if 2 vectors are linearly independent. And that's if one is a multiple of the other, right? So I don't even need to row reduce this. I know they're linearly independent because one is not a multiple of the other. So, or if you row reduce it, you get the identity and 0. So yes, they are linearly independent. The computation for does it span would go 1, 2, 1, negative 1, and then you want a general vector here. So you want to be able to express any vector in R2 as a linear combination of these 2 vectors. Well, if that matrix row reduces to the identity, so will this. So that means this will have a unique solution, right? You're not going to get a row of zeros here, so you're not going to get infinitely many solutions. So because they're linearly independent, this will have a unique solution. So this row reduces, because they're linearly independent, this row reduces to something like this. So the answer is yes, it spans. So technically, and we're going to see a theorem soon about this, technically, if the 2 are linearly independent and the number of elements in the set equals the dimension, then you can say they form a basis. So the answer is yes. Last problem here is this set a basis for M22? Well, we have here a basis for M22 that contains 4 vectors, right? And we know the dimension of M22 is 4. So dimension of M22 is equal to 4. So this does not have enough elements. So you say no, not enough elements in the set.